Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'd like to welcome you to our talk this morning. It's my pleasure to introduce Nikolai Zeldovich. Now, Nikolai has the distinction of being the only candidate I have ever invited to interview for a job at Microsoft who turned me down 2 days? 3 days before the interview and said, oh, I think I'll take this job at MIT instead. Go figure, right? Anyway, we're glad. I'm really glad to have him here. When he decided not to interview, we did decide it'd be great to have him come up and give his talk on HiStar and get to meet people. He's Dave Mazaris' student at Stanford. Or I guess you're graduated now, so you're not Dave's anymore, huh? And he's headed off to MIT this fall as a professor. So we're really quite pleased to have him here.
Thanks very much. So I'm going to tell you in this talk about how we can build secure systems out of buggy code by using this idea of information flow control. So let's see, why is it so difficult to build secure systems in the first place? Well, today, a single bug in almost any line of code in our systems can usually lead to some kind of security vulnerability. So it's not surprising then that we are seeing very simple bugs in web applications leading to disclosures of millions of social security and credit card numbers. And ironically, even security software itself often has bugs in it as well. So for example, Symantec's virus scanner, which is supposed to improve the security of our systems, actually had a bug in it that exposed 200 million machines on the internet to attack. So our current strategy for dealing with this kind of security mess is to try to come up with techniques to find and fix every one of these bugs, from buffer overflows to SQL injection attacks and so on. But in practice, this is just turning into an arms race with the attacker of who's going to be the guy who finds the next bug, whether it's going to be us or the attackers. And experience shows that we can't actually eliminate all these bugs in the first place, so this will just keep going on and on. So I claim that this strategy is simply not sustainable in the long run. So to understand this problem in a bit more detail, let's look at an example application here to understand what does it mean for a system to be secure. So here we have a simple web application such as a job search website. And at a high level, the web application itself is concerned with security of different user profiles. So for example, making sure that one user cannot look at someone else's resume in the system. One level down, the web server is concerned with ensuring which web browsers can make what different HTTP requests to the system. Further down, the operating system probably has some mechanism for protecting different Unix users from one another. And the hardware provides some hardware mechanism for protecting the kernel from application code. What all this means taken together is that if we want the whole system to be secure, code at every one of these layers has to be correct. So that even if we somehow manage to build a perfectly secure hardware platform and a perfectly secure operating system, the application as a whole could still be compromised by bugs anywhere up the stack. So this is just not going to happen, of course, because we have millions of lines of code at each one of these layers that has to be correct in the current model. So what can we do about this problem? Well, I claim that as long as the security of our systems continues depending on all of this code being correct, we're basically doomed. However, in this talk, I will try to convince you that we can still potentially build secure systems despite bugs in all of this code. So to understand how this is going to work, let's step back for a second and rethink how security should work. So at a high level, most security concerns we have in a system have to do with the data in the system, not necessarily with the code. So for example, I don't want my financial data being sent out to an attacker's website, and my password from my system shouldn't be sent to some phishing system, and one user's profile in a web server shouldn't be getting sent to a different user's web browser. Suppose we could actually control all these data movements in a system, somehow in the operating system. Then as long as our data was secure, we wouldn't actually have to care what the code was doing with our data. And this would achieve our goal of building a secure system without having to care whether the code is buggy or not. Yeah?
Quick question. apologize for that, just I came
Sure.
in late. What's the? I'm having a hard time understanding just one thing. Like, if the code is, what's the difference between being buggy and being insecure?
So that's roughly, we're assuming it's the same thing. So buggy code can probably be taken over by an attacker, and to a first approximation, we assume that it is controlled by an attacker to some degree.
Well, then by definition, isn't like buggy code insecure?
Right. So the goal of in this case, we're sort of differentiating between functionality and security. So we're saying that we'd like to build a system that might be secure, that should always be secure, but if it tries to violate security, it'll stop functioning but not break your data privacy guarantees, for example.
So you're separating security-related functionality of the code, or
in some sense, yes. So basically what we want to say is that here's a system as a whole. It's either going to perform this function or it's not going to perform anything at all. So currently we have all these data movement policies in our systems. So for example, making sure that a user's profile can only be sent to his web browser and a web server and so on. But all these kinds of policies are being enforced by code all over the place in all these different layers. And as a result, code enforcing all these policies has to be correct, as indicated by the yellow color here. So this code has to be trusted. And what I will argue for is that this idea of protecting data in a system should be abstracted into a common mechanism provided by the lowest level in a system, either by hardware or by the operating system. And the security goals of all the higher levels should be reduced to this common protection mechanism. So in particular, I will argue that this common mechanism should be about controlling data movement in a system, which actually cuts across different layers of abstraction. So what I mean by this is that if you think about data in a system, we have the same data in memory pages and in files, and can also be thought of as representing things in applications, such as your user profile in a web server or your tax information in a financial application. And what this means is that any security policy that we have about these high-level abstractions in an application can also be directly translated into data movement policy on low-level abstractions that actually store that data in hardware or in the operating system. And we can control these data movement policies at these low-level abstractions as well. And this is fundamentally what's going to allow us to enforce these data movement security policies in a small amount of code. And I will show you later how about 100 lines of code can enforce the security policy for a fairly complex application. So this idea of controlling data movement in systems has been around for a while. So it was originally used in the 70s in military systems to ensure that, top secret data cannot be written to unclassified files by applications. However, even though these military operating systems did provide an information flow control mechanism at a low level, they didn't actually allow higher level applications to make use of this mechanism. And what this means is that if we were to write a web server on a military operating system, we would have to basically implement our security policies from scratch again, making our entire software stack part of the trusted computing base. So some more recent work, such as the GIF programming language or the Flume system, has actually allowed higher level applications to make use of an information flow control mechanism. So for example, in GIF and Flume, a web application can use the information flow control mechanism provided by the underlying system to enforce its own security policies. However, in all of these systems, there are still millions of lines of code in the remaining components here, indicated by the yellow color, that have to be correct in order for the system to be secure. And what I will argue about in this talk is that information flow control should be the fundamental protection mechanism provided by the lowest level in a system, and all other protection in the system should be built on top of this one mechanism. And in this talk, I will show you how information flow control can actually be enforced by a small 20,000 line kernel, or even by the hardware itself. So, although this seems like the information flow control mechanism we're going to be talking about is actually conceptually fairly simple. So what we're going to do is we're going to associate something we call a label with every piece of data in the system. And as I mentioned earlier, this label is going to apply to data at all different levels of abstraction, from hardware to operating system to application data. And this label is going to follow the data as it moves around through the system. And ultimately, this label is going to specify what can happen to the data. So for example, it can make sure that any copy of my social security number cannot be sent to an attacker's website. And if we get this one simple mechanism right, the hope is that most of the other code in the system is not going to have to worry about security. However, even though this mechanism seems fairly straightforward, it's not at all obvious how do we build all other protection in the system on top of this one mechanism. So for example, how do we implement things like user accounts with this simple information flow control mechanism? Or if we do that, how do we give users and applications access to this same protection mechanism that's being used to constrain them in the first place? Or what happens when applications and users misuse this mechanism and create a process that they can no longer communicate with or kill? Or how do we even manage a system where the system administrator might not have the rights to talk to most of the processes on his own machine? So in this talk, I will tell you about 3 systems that we've built at Stanford that follow this idea of building information flow control as the lowest level protection mechanism and using it for all other protection primitives higher up. So the bulk of the talk is going to be about this operating system called HiStar that we've built that controls information flow in a small OS kernel. I will then also briefly mention a hardware system called Loki that shows that if we can modify the hardware, we can actually reduce the trusted computing base even smaller and enforce information flow control largely in the processor itself. And finally, I will briefly mention a distributed system called HiStar that can also extend this idea of information flow control to a distributed system of multiple machines. So let me start out by talking about information flow control in this HiStar operating system. And I'll start out with an example application of a virus scanner. So here on the left, we have a virus scanner process that reads our private data and perhaps stores some temporary state. And on the right, we have an update process that receives new versions of a virus database from the network. So I don't expect any of these processes to be malicious by design, but as I mentioned earlier, even Symantec's virus scanner was vulnerable, had vulnerabilities in it. So to the extent possible, we should probably treat both the virus scanner and the update process as malicious here. And the question is, if these guys are malicious, can we ensure that our system is still secure? In particular, can we ensure that our files are not corrupted or not sent over the network? So at some high level, this seems like the perfect job for information flow control. We want to associate some kind of red label with our private user files on the left there. It'll also be associated with the virus scanner process and any temporary state that it saves. But this label will somehow prevent the virus scanner from sending our data out onto the network. So let's see, can we actually implement such a policy in an operating system like Linux today? So what can go wrong? Well, one obvious thing is that the virus scanner can just take our data and send it out onto the network directly. Okay, so we can fix this by restricting access to sockets in some manner. But then the virus scanner can also collude with the update process, and if both of them are malicious, it can pass the data to the update process, which will then send it onto the network in turn. And this guy, by definition, needs access to the network. So to fix this, we need to somehow restrict inter-process communication in the system as well. But then the virus scanner can also write our private data into a temporary file, and the update process will read it out from there. Or the virus scanner can set its process title to the contents of your private file, and the update process will run PS to observe it. Or the virus scanner can modulate disk space usage in some detectable fashion, or lock different regions of the virus database, and so on. Or it can even take over some other unwilling process in the system using a debugging mechanism and have that process leak the data out. So it seems like this list of ways of leaking data on Linux just keeps going on and on. Is there any hope for us to actually enforce such a simple information flow control policy here? So it turns out that the problem is that the Unix interface at which I have been describing things up to this point is too high level for controlling information flow. So this Unix API, shown with this blue line on the left here, has 2 fundamental problems with it. One is that there's just too many ways for data to move around inside of the kernel, as I illustrated with all these examples just now. And the second problem is that Unix fundamentally associates protection with processes and files, not with the data inside of these objects. As a result, it's very easy for a process to launder data by reading the data from one file and writing it out into a different file with different protection permissions. So as a result, using this Unix API as the security boundary, as indicated by this red line, is simply a bad idea if we want to have any guarantees of enforcing information flow control here. So to solve this problem in HiStar, this operating system that we've designed, we split up these traditional boundaries into a lower level security boundary provided by the kernel, and the same existing Unix API will be provided at a much higher level, and there will be a Unix library in our case that will translate this traditional Unix API into our much lower level system call interface that will actually enforce security in our case. And the question here is, how do we actually design this kernel mechanism such that on one hand, the kernel is small and simple and we have strong enforcement of our security guarantees, but at the same time, this interface is actually general enough for us to be able to implement a Unix library on top of it to provide all the things we come to expect from an operating system, and to capture all the security policies we might want from this operating system as well. So at a high level, the approach we're going to take is as follows. So the kernel is going to provide a fairly simple interface that consists of 6 kernel object types. I will tell you in a little bit. And these object types are going to be expressive enough for us to build a Unix-like environment on top of them. And the only security mechanism provided by the kernel will be an information flow control mechanism. And it's going to be egalitarian in the sense that any process in the system can make use of this mechanism, not just the system administrator. And then I'm going to show you how we can build everything else in the system from these simple primitives. And what gives us some hope that we've found the right primitives is that the same set of simple mechanisms seem to be solving a whole bunch of different problems for us, as I will be illustrating in the rest of the talk. So I will start out by telling you a little bit more about these kernel mechanisms, and then I will show you how they can be combined together to achieve some interesting functionality. Then I will argue for why these mechanisms provide better security guarantees than Unix does today, and finally show you some applications of these mechanisms. So to start out, here are the 6 kernel object types that our kernel has. 4 of them are probably familiar to anyone who's worked on an operating system before. We have segments, threads, address spaces, and devices. And what this means is that we can implement all the things you come to expect from an operating system. But we also have 2 unique kernel object types that HiStar provides that are key to achieving our security guarantees. We have a gate object that provides inter-process communication for us, and a container object that is similar to a directory object in Unix that stores all other kernel objects. So every kernel object is stored in some other container. And I will describe these kernel objects in a bit more detail later on. And each one of these kernel objects has a label associated with it that provides information flow control in our case. And in particular, this label describes what the security properties of the data contained inside of that object. And the way I will describe data in this talk is by analogy of colors. So here I have a thread object in the middle and 2 segments analogous to files effectively on either side of it. And I will use the color yellow to indicate objects that have my private data inside of them. So I might label all of these 3 objects with this yellow no smoking symbol, which means that they contain my yellow private data inside of them. And the rule the kernel enforces is that yellow data can only flow to other yellow objects. So in this case, the thread can read and write both of these segments. We can also have multiple colors of data in the system. So if this file on the right is labeled purple, that means it contains someone else's private data, and the thread is not allowed to either read or write this file. And finally, we can also have multiple colors of data in the same object's label. So if the thread in the middle is labeled both yellow and purple, that means it can see both of our private data, so it can read both of our files, but it can write neither of them, because that would leak information about the other user. So this would seem to form a perfectly secure system in the sense that all of my data is perpetually labeled yellow, but at some point I actually want to get the data out of the system. So for that reason, we introduced the notion of ownership of data that allows a process to bypass this mechanism. So if this thread in the middle has a ownership of this yellow data indicated by a yellow star symbol here, it means that it controls this yellow data and can take yellow data from an object on the left and write it out into a non-yellow object on the right. So I'm explicitly trusting it to bypass these restrictions, and what the thread might do is encrypt my data, for example. So anyone in the system can actually allocate a new color in the system, and they get a star symbol, and they can then use this corresponding color to specify information flow restrictions on any data they themselves introduce. So in this sense, the label mechanism is egalitarian because any process in the system is equivalent. Anyone can request these colors, and as far as the kernel is concerned, all colors are equally powerful. So these kernel object types and these labels that I've just described to you form this entire kernel interface at the low level provided by the HiStar kernel itself. And now I will tell you how we can actually make use of this mechanism at a higher level to provide some more interesting functionality. So to start with, we can implement all the standard operating system abstractions. So for example, a Unix process in HiStar is composed of a container that has a thread executing in an address space object, and there are separate segments providing all the different pieces of memory you want. And this actually results in a fairly usable Unix-like system. So my laptop is actually running this HiStar operating system, and I can switch to a different virtual terminal and log in as myself, list my files, check that I'm running under my user account, list the running processes, and so on. So it actually results in a fairly usable Unix-like environment. But the interesting thing is that it's actually not just another clone of Unix or Linux. So if you recall earlier, we had this virus scanner example where we wanted to make sure that a malicious virus scanner could not corrupt or disclose our private data onto the network. So we can easily achieve this in HiStar by labeling my private data yellow. Then the virus scanner and any temporary data it saves will also be labeled yellow. But this yellow label will automatically prevent the virus scanner from disclosing my data out onto the network or to anyone else in the system. And the nice thing here is that there's no need anymore to audit this virus scanner code for security. The operating system automatically ensures that the only thing it can do is to look at my private data, but not to disclose it out onto the network. But there's a problem here, namely, how do I actually get the output from the virus scanner out onto my terminal, where my terminal might not actually be labeled yellow in this system? And this is exactly the reason why we introduced this notion of ownership earlier. So we have a small process called wrap in our system that has the corresponding yellow star, which allows it to declassify this yellow data and send it out onto my terminal. And this wrap process is fairly small. It's just 140 lines of code. And the nice thing here is that this small piece of code can enforce this fairly interesting security policy on a large and frequently changing application without having to understand what the application is exactly doing. And similarly, we can use the same information flow control mechanism to ensure that a malicious virus scanner cannot corrupt my private data either. So we can use a separate purple color here to label the virus scanner and my temporary files as well. And as long as my files are not labeled purple, the operating system's information flow control rules ensure that the virus scanner cannot overwrite my data, although it can still send the output to my terminal here. Question?
Can you explain a little bit about, you mentioned the PS case, right, at the beginning. You say like the scanning process.
Right.
But how do you prevent that to happen?
So what actually happens, so basically what we do in the kernel is we say we want security to take precedence over functionality in all cases. So it is up to the Unix library to implement something that looks like PS, but it cannot violate information flow control rules because the kernel enforces that. So as a result, the implementation of PS in our user space library can only list the processes you have the rights to see have existed. So as a result, when I ran PS in my example here, you only see the processes in my terminal, for example. You don't see every single process in the system because allowing you to see that might violate information flow rules. Yeah.
In your earlier example, you mentioned hidden channels like filling up the disk.
Yeah.
So another update process in the system couldn't stat the disk and see its size.
So we don't allow any process. We have no notion of kind of how much space there is or how much space has been taken up. We have a notion of quotas, but those are designed in a way that I will describe maybe later, but they don't actually leak information. So we've actually implemented this wrap application that I just mentioned earlier. So this wrap program can run any standard Unix application you want that runs on HiStar, but it provides these two extra security guarantees that you cannot get on Unix today. In particular, the application you run is not going to be able to corrupt any of your files, and it's not going to be able to disclose anything onto the network. And it does this by setting this label on the application and running it, and this is all done in 140 lines of code. And the kernel then does all the heavy lifting, if you will, of enforcing the security policy. And all of this together can enforce the security policy on any application. So for example, I can run wrap on simple commands like ls, and it seems to work. I can also run wrap on this virus scanner I downloaded from SourceForge, and it seems to scan my home directory for viruses and doesn't find anything. But the interesting thing here is that I don't actually have to trust the virus scanner to do the right thing here. Even if it were trying to be malicious, it wouldn't be able to corrupt any of my data or to disclose my mail to some Hotmail account or anything else like that. So in particular, if I get this mystery shell script from a friend of mine that on a Unix system would disclose my private key and remove my home directory, if I run it under wrap, automatically nothing bad can happen. It can't actually create any files in a public directory, and it can't actually modify my home directory or any of the files in it. So, yeah.
I mean, based on you just said about the disk, the quota, so you are trying to prevent the covert channels.
Yes.
But do you think you can prevent all covert channels?
So what we aim for is that we want to ensure that our design has no covert channels in it. And what this means is that, of course, our implementation will have various kinds of covert channels in it. But because the covert channel is not inherent in the design, we hope to be able to fix any particular covert channel that bothers you without breaking applications. And this means that you can kind of tweak the security knob, if you will, at runtime without having to redesign your whole system to increase security.
Adding to his question, it seems that if you're not controlling the hardware, you're not going to be able to stop all of these hardware-based covert channels, right?
Fundamentally, yes. If you have a single operating system running multiple levels of security levels, you're going to have various, some covert channels are going to be unavoidable. And what we want is basically a design that has no inherent covert channels, which means that for any covert channel bit rate that you would like to achieve, it is theoretically achievable by modulating these covert channels in some way or mitigating them without having to break applications. So you can maybe allocate a separate CPU for every process, or maybe you have to have very coarse-grained scheduling or flush caches on every context switch. But you can do this and pay a performance cost perhaps for security, but it doesn't require a redesign.
This might just be a failure of my imagination, but I'm having trouble seeing how this would help prevent something like a SQL injection attack, where you have a process that gets some data over the network, does some high-level semantic processing on it, and then decides to froth a database. It seems like if you're just at the sort of label view, the same thing is happening if I've gotten a request and do a good update of the database versus gotten a request and have done a malicious update of the database. It seems like in both cases, none of the actual data from the request is necessarily going into the database, but you might at a high semantic level have told the database to do something it wasn't supposed to do, like drop a table.
So what we'd ultimately like to have is to express security properties using these labels. For example, that a regular website user shouldn't be able to drop a database table. Or for example, if you're doing a select query on a database, we'd like to associate a different label with every user's row in the database so that the application can be malicious and send all kinds of select queries at once. It needn't even be a SQL injection attack. But the output from the database comes back labeled, and you can only send the right user's data to the right user's web browser. So it's kind of an end-to-end.
At some level, there's going to be some shared state though that you can't apply labels to. In other words, even if you were to individually label every row, there's going to be, let's say, some metadata about the database or something which all users have to modify. Whenever anybody inserts a row into a database, there's some structure that describes the database that has to be modified. And
right.
So if you drop a table, you might just be modifying that shared metadata and not any individual row.
Absolutely. And at some point, yes, we have to have some code to be correct in this case. And what we're really going after is that we want to have minimize the amount of trusted code for any particular action here. So ultimately, yes, we need to have some code that manages the set of tables in the database and the schema for all of them and so on.
Code, though, you're talking now about the TCP also including application code and not just the
The
operating system.
TCP for that particular application will include some of its own code, or the TCP for the database, for example.
So there are some places where we need trusted code higher in the stack, I think.
Absolutely. So something has to do something correct. And what we'd really like to do is to provide you the mechanism to have a small amount of code enforce a security policy for a much larger application. So for example, this wrap program has to be correct. Otherwise, it can do anything with my privileges and send my data anywhere it wants. But the nice thing is that this 140-line wrap program can set up these labels and then run the application in a way that enforces security regardless of the size or the intentions or the complexity of the application. And hopefully the same can be the case for a web server. And we actually have a web server I'll show you later. It doesn't have a SQL database per se. It uses the file system. But I think the same ideas will hopefully apply there. So you will have to trust some part of the database, but not the entire database, hopefully.
So wrap is part of the HiStar trusted code.
So it is a program that's not part of the fully trusted kernel. Whenever you invoke the program, you are trusting it in some sense with your user privileges. So it's like a program in Unix, right? So you run ls, you're trusting it, but it's not part of the TCB if you don't run it, right? So it's not a part of the TCB for the web server, for example.
So wrap itself has no special permissions.
So wrap itself has no special permissions, and in fact, if I might have two versions of wrap, I can run wrap ls, and the first wrap is trusted, the second wrap is not trusted, and the ls is kind of twice isolated. So it's kind of.
Does that mean if I have wrap, I can run a legacy application without that legacy application doesn't have to understand the labeling?
Exactly. So this ls is actually the GNU core utils ls that I haven't modified in any way. I just recompiled it for HiStar. So we have a POSIX compatibility that allows us to do this. So legacy applications that need persistent data, for example, will need a slightly different wrap that enforces a different security policy that it actually allows data to persist between invocations, for example, but it will also be fairly small. Question?
Just out of curiosity, earlier you ran ls without wrap, you still got output? Is that when you first?
Sorry?
You ran ls or p?
Yeah, I can run ls.
Okay, so you don't need wrap to get that out?
Right.
Okay.
Yeah, so basically, if I don't run wrap, everything, it doesn't get any kind of colors. It gets my stars representing my privileges, but it's not restricted in any way. So,
That's the way
right, so this ls could do anything it wants.
So it's still getting your stars, but you're just...
Exactly, yes. But wrap gives it my stars, but also restricts it in some way. Yeah.
One more question about wrap.
Yeah.
Presumably, like HiStar could have mechanisms that would test the integrity or identity programs that you have allowed to operate from your TCB, like certificate validation, things of this sort.
So the operating system doesn't have any mechanism for kind of a testing for user space programs. You can do it yourself, though. So for example, you could modify the shell to read the SHA-1 hash of a binary before running it. And executing a binary is all implemented in the user space library, so you can ensure that the same binary you checksum is the one you load into an address space and start executing. So you avoid time of check or time of use problems by the fact that the library is in fact loading the executable and creating the address space and so on. So now let me move on to this question. Yeah, sure.
During these demos, have you ever accidentally run mystery.sh without wrap?
Not during a practice talk I did, but it's recovered. Yeah.
That's why it's going to MIT.
Yeah. So now let me move on to this question of how do we know that, why is HiStar providing better security than Unix here? So let's take a look at another example of the way information can leak in a Unix system. So here we have the same virus scanner process on the left and the update process on the right, and we want to make sure that the scanner process can't leak data to the update process here. And suppose the kernel can actually enforce this guarantee. But what happens if these two processes share a read-only file descriptor, perhaps representing the virus database? So this might seem like a reasonable configuration because the file descriptor is read-only, so neither guy can write to the file. But it turns out that each file descriptor in Unix has a seek offset associated with it. So the scanner process can potentially seek the file descriptor back and forth, and the update process can look at the seek pointer and say, aha, that's the information you're trying to leak to me. So the reason this is a problem in Unix is that these file descriptors, along with all these other kernel abstractions, process, titles, file descriptor, file locks, and so on, are implemented as part of the kernel inside of the trusted computing base. So you have to get every one of these abstractions right in order for your security to hold. And the way HiStar gets around this problem is by implementing all these different abstractions in the Unix library above the security boundary. So as a result, we don't have to reason about all these different abstractions in order to enforce security correctly. So in particular, this file descriptor problem is not a problem on HiStar almost by design, in the sense that every file descriptor in HiStar is implemented with a separate segment object that stores all the state associated with the file descriptor, including the seek pointer. And if the scanner process on the left were to be labeled yellow, it would automatically not be able to update any of the state in the file descriptor segment because of a single access control check enforced by the kernel, namely whether information can flow from one object to another. Or in other words, just object read and write checks. So in this way, we can actually, so these labels then become the only security building block we need in the operating system to enforce security. So on one hand, it's a very low-level mechanism in the sense that it just controls when information can flow from one object to another. But it's also a very expressive mechanism in the sense that it allows, it can be used in our case to implement both Unix user IDs and group IDs and all the things you expect in a Unix system, and can also be used for things you cannot even implement in Unix. For example, security policies of this wrap application I showed earlier. And this label mechanism is egalitarian in the sense that it allows anyone to allocate a new color in the system and get the corresponding star and specify more information flow restrictions as they would like. And in fact, the system doesn't even have any inherent notion of superuser privileges for the system administrator. So this is not to say that we don't have a system administrator in our system. Of course, we need some guy to have privileges to back up our data or to reset our password if we forget it. But we do this all very explicitly in HiStar. So if we have two users, Alice and Bob here, each with their own privileges indicated by the yellow and purple stars, they very explicitly give their privileges to the system administrator's shell so that he can back up their data. But if the user Bob here on the right wants to have some secret data that's not accessible to the system administrator, but the privileges of this system administrator are all implemented by convention inside of this Unix library above the security boundary. So that if the user Bob here on the right wants to actually have some secret data that's not accessible to the system administrator, he can easily do so. So, for example, if he has this SSH agent process that on Unix holds your private key for authenticating to other machines on the network, he can easily label it with some new green color. And as long as he doesn't give the corresponding green star to the system administrator can't get at his private key. Now, of course, there's a potential problem here. Namely, what happens if this SSH agent process goes nuts and allocates more colors and refuses to talk to either the user or the system administrator and starts using up CPU cycles? What can we actually do about this process at this point? So the way we solve this in HiStar is by very explicitly controlling all resource allocation. So every user in the system has a home container, analogous to a home directory, that stores all of the kernel object representing their processes and files. And when user Bob here starts a new SSH agent process, it starts inside of his home container. And at this point, even if this process allocates a whole bunch of different colors that prevent it from talking to anyone on the system, the user can still delete that SSH agent process from his home container, and the kernel will then garbage collect it for you. And in fact, this garbage collection mechanism, or this container mechanism, is also what allows us to manage the system without any superuser access. So in HiStar, the only special privilege that the system administrator has is access to the top-level container in the system. This means that the system administrator can give out resources to different users by creating subcontainers and can revoke those resources by deleting those subcontainers. But it does not give the system administrator the right to look at the data inside of those containers. What this means is that even if the system administrator's account is compromised, the worst thing that the attacker can do is to either reclaim all resources or to give himself more resources. He cannot compromise the data of other users on the system. Question?
Does the administrator have the privilege to install drivers like for the disk and the network?
In our case, he does not. So there's no loadable kernel modules in HiStar at all.
Super administrator now that is configuring the system.
So there's some guy who has physical hardware access, and we don't try to prevent him from compromising the system. So for example, when you install HiStar initially, you of course install some kernel, and that has to be correct. And we don't try to solve that problem. You could, have some checksum in the BIOS that make sure you have a signed kernel or something like that, but at some point you have to have a root of trust, and in our case it's the kernel.
Differentiate, after HiStar is running, you differentiate that one guy have physical access to install driver, but the other guy remotely cannot install driver.
Well, what differentiates them is the fact that the guy with physical access can put on a CD and reboot the machine and boot off the CD to,
It only can happen at a certain rates.
So in fact, the same container mechanism also allows us to implement the file system in HiStar as well. So of course, you need some sort of mechanism to store data persistently in an operating system to implement the file system. But the way Unix does this is by providing two very different mechanisms for storing data in memory and on disk. So in memory, you call malloc or break to allocate pages of memory. But on disk, to allocate the space there, you open a file, you call read or write, and then close the file descriptor. What this also means is that there's also two very different ways of protecting data in memory and on disk that are not the same in Unix, and it's actually difficult to understand what are the protections of data when it bounces back between memory and disk. We actually solve this problem in HiStar by reusing the same exact mechanisms I've been already telling you about to implement the file system as well. So the only thing we need to do in HiStar to implement this is to provide a single level of storage, much as in Multics or Eros operating systems in the past. And what all this means is that all the kernel objects I've been talking to you about are stored persistently on disk, and their in-memory version is just a cache of their disk contents. So once we have this idea of a persistent store, we can implement the file system with these same kernel objects. So directories are implemented by containers, and every container has a special file name segment that maps file names to the actual objects implementing that file. The nice thing about implementing the file system with the same abstractions is that we can use the same protection mechanism for file system security as well. So if I want to make sure that my mail doesn't end up on my website, I just label my mailbox segment with, for example, this yellow symbol, and the kernel will automatically ensure that my mail cannot end up in my public HTML directory then. And one other nice thing about a single level store is that it also allows us to avoid superuser privileges for the system administrator. So on Unix, the root user needs superuser privileges to start everything when the system boots up. But on HiStar, processes don't actually notice a hardware reboot because of this single level store. So I will quickly demonstrate this here. So if I try to reboot my machine, I have to log in as root. But if I type reboot, what's actually going on is that the kernel is now checkpointing all the kernel objects implementing this Unix environment to disk. And when it writes them all out to disk, it will physically reboot my machine. And at that point, when the kernel boots up again, it will restore the Unix environment. Well, I'm sorry for the misimaging, but so when the kernel boots up again, it'll resync at some point, hopefully. Sorry. So when the kernel comes back up, it basically reads the whole environment back from disk and continues executing exactly where we left off. So the nice thing is that, for example, if you remember this user that had an SSH agent process running, this SSH agent process will continue running without any need to trust the system administrator to restart it when the machine reboots. Question?
How are you dealing with consistency of the now that you basically have an object store on disk, dealing with consistency of the objects if, let's say, HiStar crashes?
Yeah, we have write-ahead log, we have dirty bits in memory, all the usual tricks, yeah. Right. So, of course, we want to reboot the machine sometimes for management reasons if some software is running away and using up all the CPU cycles. And we can do this in HiStar as well. It's just that we have a separate command for doing it. So we have a command called ureboot that can reboot all the user space code in the operating system without having to restart the kernel. And all it needs to do is just to delete all the process containers in the system while keeping the file system containers intact and start a new init process. And in a few slides, I will show you how a gate mechanism can actually allow this init process to also operate without having to require any superuser privileges as well. So now let me move on to the question of how do we know that HiStar is enforcing any of these information flow control guarantees correctly? So what gives us some hope is that information flow control gives us a very precise security goal of what do we want to achieve, namely that whenever information flows from one object to another, all we need to do is to compare the labels on those two objects to understand whether the operation should be allowed or not. And this means that we can very precisely understand, we don't have to actually reason about higher level semantics to understand what security checks should be performed. And of course, the long-term goal here is to actually verify the security of our implementation. And unlike Unix, we actually have a very precise security goal in mind here. And we've done some model checking and static and dynamic analysis to try to do this. But in the meantime, of course, we haven't verified HiStar fully yet. But in the meantime, our question is, how do we ensure that at least our design of the operating system here is sound? And in the context of information flow control, this boils down to the question of what do we do about these covert channels in the system? So in HiStar, we classify covert channels into two broad categories. One is implementation covert channels that are not part of the specification. So as I mentioned earlier, these kinds of covert channels are nice in the sense that while they're probably unavoidable, applications, or at least well-behaved applications, don't depend on the presence of these covert channels. And what this means is that we can mitigate them or somehow introduce noise in the system to reduce their bit rates and so on without breaking these well-behaved applications. So a much more troublesome kind of covert channel, of course, is ones that are inherent in the specification of the system, because these kinds of covert channels we cannot mitigate or avoid without breaking applications. And the way HiStar deals with these covert channels is by, the way HiStar avoids these covert channels is by very explicitly labeling everything that's part of the specification. So we have a label attached to every kernel object, we have a label for every resource in the system represented by containers and so on. But there's a potentially subtle problem here, namely what do we do about the label of the label itself? So if you remember earlier, we had this example of a file descriptor associated with a Unix a seek pointer associated with the Unix file descriptor earlier, and potentially a user can modulate the label much the same way he can modulate the seek pointer to leak information. And to illustrate this problem, I will give you this example of a malicious secret process on the left that has a secret bit of data it would like to leak onto the network. And, well, suppose we label it yellow to prevent it from doing so. Turns out that in many systems, it can still leak this one bit of data out onto the network with the help of two colluding processes. And the way it does so is by sending a message to one of the two processes, depending on the bit it would like to leak. So oftentimes, sending a process in our operating system that provides information flow control propagates the label to the recipient process. So in this case, colluding process 1, which receives a message, becomes also yellow, and it can no longer talk to the network as well. So any network attacker can now say, aha, well, colluding process 1 cannot talk to the network. That must be the bit he was trying to leak to me. And in this way, we can actually bypass this information flow control restriction. Turns out that this problem has actually been kind of a thorn in the side of information flow control for a long time, and a number of systems have tried to deal with this. So for example, programming languages like GIF rely on compile time checks to avoid these problems. So if there are no checks at runtime, you cannot leak data this way. But turns out that compile time checks are too restrictive. They cannot allow such dynamic applications like the wrap example I was showing earlier. And some operating systems like IX or Asbestos give up and say, well, this is an inevitable property of dynamic labeled systems. Turns out that they just didn't quite find the right abstraction to provide in the kernel to enable this functionality. And military systems that, of course, care very much about avoiding covert channels use fixed labels on everything to ensure security. But they can only do so because they have very few labels in the first place. They just have secret, top secret, and so on. And they cannot implement very dynamic applications like this wrap example either. So the way HiStar avoids this problem in its design is to have immutable labels for all non-thread objects in the system. This means once the object is created, it has a fixed label, and the attacker cannot modulate that label to convey information. But because immutable labels are too restrictive for our dynamic applications, we actually allow threads and only threads to change their own label. And the reason it is safe for a thread to change its own label is that any information that goes into this decision for a thread to change its own label is already available to the thread, so it can leak it directly. So it doesn't hurt us to allow it to change its label just the same. And of course, we only allow a thread to add or not to remove categories from its label to ensure that it cannot uncolor itself in some sense. So to show you how this simple idea of allowing a thread to change its own label allows us to implement all kinds of interesting application behaviors we want, let's take a look at this example of a job search website application here. So on the right here, we have a database server process that has a database of job listings. And on the left, we have a job search process that would like to query this database for potential job openings. And what we'd like to make sure is that the fact that this guy is looking for a job is not revealed to anyone in the system, not even the database itself. And we'll ensure this with this yellow label on the job search process itself. But how can these two very differently labeled processes communicate with one another if they cannot change each other's labels? So the way we achieve this in HiStar is by using this gate abstraction I briefly mentioned earlier. So what this gate abstraction is going to do is that when the job search process on the left sends a query to this gate object, it's going to switch the client's own thread into the address space and protection domain of the database server process. So what this means is that this client thread is now running in the database server's address space with its privileges, and it can now read the job listings database, process the query, and send the results back to the client's own address space, all without having to ever change the label of any thread other than the client's thread itself. So in this way, we can actually achieve inter-process communication between differently labeled processes without having to change the label of anything other than the client's own thread. So in fact, this gate mechanism also helps us avoid superuser privileges for restarting applications as well. So if you remember earlier, we had this reboot command that killed all the processes running in the system, but there's no need to kill gates because they're passive objects that are not actually using CPU time actively. So a reboot command actually leaves the gate objects intact, which store the privileges of the database server across process restarts. So to summarize the design of the HiStar kernel, is that I've presented you a very small number of mechanisms, I hope, that seem to be solving a whole bunch of different problems for us. So this container mechanism I showed you allows us to control the allocation of resources in the system and implement the file system. And while I didn't actually mention it, it allows us to discover the labels of other objects in the system as well. And this gate abstraction allows us to implement inter-process communication with immutable labels and allows us to avoid superuser privileges in the system. And these labels themselves are very versatile in the sense that they allow us to implement Unix users, this wrap application example, security of a database, and as I will show in a little bit, the security of a web server as well. And all of these abstractions are provided by a small 20,000 line kernel that everything else builds on top of. So as I'm running out of time, I will quickly go through a couple of applications. So I will tell you largely about how we can actually build a web server out of untrusted code in HiStar. So here's the architecture of a traditional web server like Apache on Linux. So there is some process that accepts connections from the web browser, hands them off to an OpenSSL library for decryption. Then the plain text request is passed on to a component that parses the HTTP request, which then in turn maybe runs some applications. In this case, maybe generating a PDF file using GoScript. So all of this code put together is about 1 million lines of code that have to be fully trusted in order for the web server to be secure. So if any line of 1 million lines of code here were malicious, it could disclose the information for any one of these users. So we can greatly shrink this TCB on HiStar by, for example, labeling each user's different data with a different color here. So then if we run a separate instance of the application code labeled with that user's color, we can ensure that the only way this data can escape is through a component that has the user's corresponding star, which in this case would be this HTTP parser. So as long as this HTTP component were secure, even a malicious application code could not disclose one user's data to a different user's web browser. But this is potentially problematic in the sense that this HTTP component now is fully trusted. We can avoid that on HiStar as well by breaking out the user's privileges into a series of different authentication agents, one per user. So if we have a separate authentication agent for every user, we can spawn a separate instance of this HTTP process, and it will explicitly authenticate each user by sending the user's password to the authentication agent and getting the privileges back. So now we have no fully trusted user code in this application.
But if I want to leak information, I can still leak it out by sending, say, an image request where the image request goes to my server and the query string for the image has all the information I want to leak out.
So the threat model here is this application kind of being malicious. Or you mean sort of giving a web page back to the web browser that then performs something else.
Elsewhere.
Right. So perhaps in this case you can enforce that the object returned has to have file type PDF or something along those lines, or perhaps.
Okay.
So of course that's a valid point, and kind of the end-to-end goal in our case is to be able to label parts of the document as well, so that you know that, well, this part of the HTML document was synthesized by the application, so I shouldn't trust it as much, so I shouldn't send any of this data to outside servers. So if we can extend this idea of information flow control into the web browser, where we can label different parts of the HTML DOM, hopefully we can solve that as well. So that's kind of the information flow control view of this problem. So we can also ensure that the OpenSSL library is not part of our trusted computing base either. So if we label each instance of the OpenSSL library with a different color, one per TCP connection, we can ensure that even if the OpenSSL library is compromised, the worst thing it can do is send your data unencrypted maybe to your own web browser, but not your unencrypted data to someone else on the network. Question?
All right, another quick question. How does the HTTP module know what information is safe to classify?
So the guarantee we're going for here is kind of ensuring that kind of any data generated from your data only ends up with your web browser. So it's kind of connecting the pipes in the right direction or connecting the dots the right way, not necessarily interpreting the data along the way. So you could, of course, try to do some data interpretation, but that seems much more prone to error. So this is a very limited property that we're achieving here. So we can also ensure that the SSL library can disclose your private key either by having a separate RSA daemon. But as I'm running out of time, I'll just say that basically what we can do here is by using information flow control, we can enforce the security of this web server in a fairly small fraction of the overall size of the web server. So we can enforce these data flow security properties in about 6,000 lines of trusted code out of a total of 1 million lines of code here. So I'll probably stop here rather than bore you to death. Okay, I thought it was an hour long. All right. All right, sounds good. So it turns out that actually not all of these 6,000 lines of code have to even be implemented specifically for this web server. So because the label mechanism is actually egalitarian, we can actually reuse the same authentication component I mentioned earlier in the web server for authenticating Unix users as well. So these authentication agents I mentioned earlier have a very simple function. They store a particular colored star and they give it back to you if you provide the right password. They don't actually care what this color is used for, whether it's a web server user or a Unix user. And in fact, we use the same exact code line for line for both the web server and our Unix library. And one nice thing is that because these labels are egalitarian, we can actually have some interesting functionality here. So for example, because each user controls their own authentication agent, we can actually allow each user to supply their own password checking code. So if you want to accept one-time passwords or implement a challenge response scheme for login, you can do so without having to get the system administrator's approval or having to get your code verified in any way. Now, of course, this introduces a potential problem, namely, what happens if you mistype your username and give your password to the wrong authentication agent in the system? And it turns out that information flow control can also solve this problem as well, because we can ensure that the authentication agent you send your password to can only give you back one bit of data, whether it's giving you the star or not, and cannot leak your password or anything about it to anyone else in the system. So to summarize, I've shown you how this information flow control mechanism provided by an operating system can actually help an application, can actually help us enforce application security guarantees in a small amount of trusted code. So what we need is a small part of the application to specify the security policy in terms of labels. So I showed you how about 6,000 lines of code can do this in a web server, and about 140 lines of code for this wrap example I showed you earlier. And then what we need is a 20,000 line kernel that can enforce these security guarantees for a wide range of applications, from the virus scan I showed you earlier to ensuring password secrecy during login, or the privacy of user data in a web server application as well. And then the nice thing is that the rest of the application code in the system can be buggy to a first approximation without compromising our security guarantees presented here. Question?
Like a social engineering attack, like I'm a user, I download a file, I want to run, at least that program would want to have my own privilege. Mm-hmm. And then that program may encrypt all my file and throw away the key and send a destruction email saying, Give me $100, I'll give you a key.
Right. So we don't have kind of an end-to-end solution for that problem. But what we do, I think, have is a mechanism that hopefully makes it easier for application developers, such as the web browser that downloaded that application in the first place, to specify certain security policies on the application when you run it. So maybe when you download arbitrary code, it first gets run in wrap, and for most applications that might be okay. Or maybe we have to extend wrap in some sense to provide a separate data store for every single application, so that it can store its own data persistently but not touch other applications' data and so on. So of course there's some trade-off of the user having to run everything in wrap, or maybe everything gets run in wrap by default and the user needs some escape hatch to store data persistently or so on. But I think we're in a better shape because this mechanism does give you this power of being able to run kind of applications you don't understand and still get some guarantees of what they're doing. So I will very briefly mention what we did in hardware. So we can actually, by using tagged memory in hardware, we were able to push a lot of these information flow control policies into the processor itself. So what our hardware does is associates a 32-bit tag with every word of memory in the system. And we have a small security monitor now running underneath of the kernel, which translates our labels into tags on physical memory. And what this means is that now we can enforce security in about half the amount of trusted code that we had before. So instead of about 12,000 lines of code in the kernel, we have about 5,000 lines of trusted security monitor code, which runs underneath the kernel that enforces security on physical hardware, physical memory. And the kernel is relegated to just minimizing covert channels at this point. So if you compromise the kernel, you get a bigger covert channel, but you don't compromise Unix file permissions, for example.
But the low key needs to understand some OS abstraction, I mean the OS state, right?
So it does not need to really understand it. So what the kernel does is actually, whenever it allocates memory or relabels memory, tells the security monitor, hey, here's the label for that piece of memory. And the security monitor translates the label into a tag on the memory and maintains a mapping between the tags and the labels. And enforces just kind of tagging on memory and implements a context switch operation.
But how does the low-level thing like a low key to tell, oh, this process is the owner, or this part of kernel is the owner of this tag?
So it all comes about through this egalitarian mechanism of how these colors get allocated in the first place. So anyone can say, hey, I'd like a new color. And this actually gets passed all the way down into the security monitor. And the security monitor now knows, hey, this process now owns this color, now has this star. And it only allows now that process to declassify that data.
Yes,
so the security monitor has the notion of a context switch now, of course.
Yes, so the low key needs to understand context switch.
Yes, it understands context switches, yes. All right. I think you have.
How far does this go to? Do you keep certain colors with registers in the processor? Or?
So we don't actually label registers themselves. We label the entire kind of register set with one value, as the current PC counter basically accounts for all the registers as well. So I think so the guys I worked with on this, Mike Dalton and Hari Kanan and Christos Kozirakis, have a version of this that has a much more finer grained tracking of data through registers and so on that works better for some cases. Turns out to have inherent covert channels that we're really trying to avoid here, and that's part of the reason why we don't actually label individual registers.
So how big is the color space and how are they allocated?
So the color space in HiStar is 2 to the 61 for various reasons, but it's nearly infinite. So the monitor actually corresponds these tag values with labels. So labels in our case are kernel objects, so they have some physical memory address. So our tag values are actually the physical memory address of the label object. Of course, the space of our tag values is 2 to the 32. It cannot possibly encompass all the possible labels we can construct. But all the labels active at any given time have to fit in your physical memory. And as a result, the 32-bit tag space is sufficient for them.
And they're allocated randomly?
Yes, so our color values are allocated by block cipher encrypting linear counter.
So the color, can I create a covert channel by allocating colors until I get the right combination of colors?
So that's the hope, is that by having a Blowfish block cipher encrypt a counter, hopefully the values are effectively PRNG. So hopefully there's no prediction. Of course, you know that once you
take one if it fits the data I want to transmit, keep it. If not, give it back.
So you don't give it back. So the counter, so the kernel just keeps a counter that forever keeps incrementing. So the colors are never reused. So there's no way to give it back. You can drop the star, but the color value never comes around again.
Right. So I can drop the color, right?
Right,
so
but no one else will get it.
Right. I was just thinking, could I create a covert channel, which is the set of colors, the colors I have right now. Is the highest one, is the last bit a 0 or a 1, and I allocate colors until I get one of those.
You can do that, but no one else, if there's some restriction on you that prevents you from leaking data, which is presumably what you're trying to circumvent, then that restriction will prevent other people from looking at your label as well.
Okay.
So whatever colors you allocate, no one will know what you kept, what you threw away.
Okay, so your colors aren't knowable to everyone.
Right.
Okay.
Right. And finally, so we actually extended all of this information flow control to distributed systems as well. And the high-level idea there is that you can basically encode these labels in network messages and have each machine enforce these information flow restrictions locally. And this actually turns out to require just about 5,000 lines more lines of trusted code on each machine to translate between the network and the local operating system representations of these information flow restrictions. And of course, we have to have some mechanism to figure out which machines are trusted to handle what data. And I will be happy to discuss this more with you later, but we had a paper at NSDI that describes how we do this. And this actually allows our HiStar web server that I described earlier to scale to multiple machines by just trusting this extra 5,000 lines of code to transmit labeled messages on the network. So to summarize, I've shown you how we can use information flow control to build secure systems out of Buggy code by providing information flow control in all these different kinds of systems. So thanks for your time. We have a bunch of papers, some live CDs of this operating system, all the source code available on our website. Thanks. Question?
So as far as some applications like say Outlook, I want to occasionally let it leak my own data when I send an attachment to somebody. Mm-hmm. So I mean, how would we apply this model to say Outlook? Would we make like a small subcomponent that has like say the yellow star that's only, I trust that to leak my data when I want it to?
Right, so perhaps one analogy is the file selection dialog would have some privileges so that if the user explicitly selected a file in that application, then that file gets declassified for that application. So you have to kind of basically declassify based on the user's intent somehow. So,
I mean, so then if say the untrusted portion of Outlook, if there was someone malicious wanted to email all of my documents, there would still have to be more of the user saying, oh no, I really don't want that to happen.
Right. Yeah. So if there's some so maybe it tries to say, well, would you like to email this file? And right. So I don't know. I mean, maybe the users will end up saying yes anyway, but I don't have an answer to that.
It's still dependent, in some cases, the user doing the right
Absolutely, yes. So at some point, we want the user to be able to get his work done, and we have some mechanism to allow that, namely the star, and someone gets it. I don't know what the right UI is for. Maybe like drag and drop is better than the file dialog, so that you can't prompt. I don't know.
So I had a question. Yeah. When we were talking about the programmable password modules and about you could label it so that it only had one bit of information to give out, which is start. So how would you do, say, logging? So I want to log how many invalid passwords.
Right, so actually that's the cool thing. So we have this fairly elaborate scheme there that actually we have a 3-phase login. So first you say, hey, I'd like to log in. And what it does is it creates a set of gates for you that you can then use to log in, and then it logs this attempt. And then one of the gates you invoke with a label that prevents it from leaking your password anywhere, and that gate checks your password. And then it gives you back an intermediate star that says this star is basically good for the real star if you give it to this other gate, which will log the fact that you logged in successfully. So you then give this intermediate star to this third gate, and it says, okay, I've logged your successful login attempt, and I'm giving you back the real thing. So it turns out you can do this. It just takes a little bit more construction. So.
In the web server example, you had OpenSSL, and it was like a largely trusted thing. And supposing OpenSSL had a bug that it used only a 0 for the symmetric key, is there any protection against such a
So that seems very difficult to predict in in our model. So all we're really going for is that kind of the data flows to the right destination. It's hard for us to kind of understand what the semantics are. So of course, yeah, if it doesn't encrypt at all, or if it has a poorly seeded RNG, then yeah, we're in trouble.
Checker that always succeeds, right?